Okay, so math time. Yesterday I finished doing the notes for this week. I added a full extra little section on global or absolute extrema because people were asking about it last time, and I figured it was nicer to just split up the notes for you. It's very short, and we already briefly talked about it. It's basically when you have a plot, the largest point throughout the entire domain of a function would be the max, and then, vice versa. The lowest point throughout an entire domain of a function would be the global min. Global and absolute are used interchangeably, by the way. And I put a note here, sometimes the absolute or global extrema is also the local one. And an example of this is the parabola, for instance. So if you only have one extrema, then it's technically the global and the local, or the absolute and the relative, whatever phrasing you prefer. The extreme value theorem, this is actually used a lot within different areas of mathematics because it tells you a way, or it gives you a way to tell if a function has extreme values or not. So it's very useful to use in other proofs of theorems for calculus. And the extreme value theorem says that, if you have a continuous function on a closed interval, then f will attain a global maximum or global minimum value within that interval. So basically, if you take a function and you restrict its domain, making sure it's continuous everywhere, there will be an extreme value basically at the top and the bottom. And now how do you find these extreme values on this interval for a function? There's this method called the closed interval method, and it's very similar to what we've already done. To find extrema in general for a function, we take the derivative, we set it equal to 0, and we find these critical numbers. Now, for the global extrema, remember, we need continuity on the entire interval where we include the endpoints. So once you have these critical numbers, you're going to find your values of f at these critical numbers, and then you're also going to check what f is at the endpoints. And then whatever value is the largest, it's going to be the global max. Whatever value is the smallest, it would be the global min. And I give one example here. One of your assignment questions is very similar to this. You have a function, and it says find the global extrema, and I think it's between -5 and 5 or something. So very similar example. We first say that, okay, since this is a polynomial, we know it's continuous throughout this entire interval, so we can use this closed interval method. Okay, there's a mark assigned for justification, so make sure you justify why we're allowed to do this. And then we find our critical numbers. So take our derivative, set it to 0, we're going to factor, and then this gives two critical numbers, x is equal to 0 and x is equal to 2. And then since we have those critical numbers, since the values are within the actual interval of interest, then we'll put these numbers into f and see what we get along with the actual endpoints. If we got a number, say I got my second critical number was 6, for example, 6 is not within this interval, so you disregard it. So assuming your critical numbers are within this actual interval, then you would include them in the possibilities of your global extrema. And so then in the problem, I just plugged in the different values. I look at my outputs and I say, okay, what's the biggest one? Well, 17 is the biggest. It corresponds to 4. So that's going to be my global maximum. And what's my lowest one? Well, that's -3. That corresponds to 2. So that's going to be my global min. And I just put a remark here. Notice that one of these are an endpoint. One of them's a critical point. And I included the graph just so you could see what the function looks like to build some intuition.